Let's try to solve this question here. You want to study a biological specimen by means of a wavelength of 10 nanometer, and you have a choice of using electromagnetic wave or an electron microscope. So if you use electromagnetic wave, probably it's a visible light microscope, the optical light microscope that you're used to. If you're using an electron microscope, then it can be transmission electron microscope, the TEM or the SEM, the scanning electron microscope, so on and so on. There's many types of microscopes actually. But what you do is you want both of these microscopes to be using the same wavelength. So if you're using optical microscope, it will be the light. So your light will have wavelength of 10 nanometer. You can think of it as light, 10 nanometer. So probably not in the visible light range, somewhere around ultraviolet or X-ray, I'm not sure, maybe X-ray. Okay, if you're talking about electron microscope, then you're using electron and you want the electron wave to be having a wavelength of 10 nanometer. Okay, electron wave might not be familiar to you, but if you think of electrons to be having wave properties, then we call it as electron wave. Okay, so they want you to find the ratio of the energy of the 10 nanometer wavelength photon to the kinetic energy of the 10 nanometer wavelength electron. So for question A over here, they want a ratio, so you divide it. You're going to divide the energy of the photon. Photon is represented by the symbol gamma. Okay, even though gamma, you might think of gamma ray, but gamma ray is a part of the electromagnetic spectrum, right? So for all types of photons, we just represent it by gamma. It's a symbol that we usually use in particle physics. Okay, so any kind of light, photons, we represent it by a symbol of gamma. Okay, so they want to divide it, or they want to find the ratio of it to the kinetic energy of the electron. Okay, so let's try to get the equation from both situations. So photon here is a light, so light for its energy can be related to wavelength using this equation hc over lambda. So this equation is quite straightforward, hc over lambda. But to obtain the equation to relate between the electron's kinetic energy to its wavelength, you have to go through kinetic energy, momentum, then wavelength. So let's probably derive it outside. So K for electron will be equals to, you start with P squared over 2m first. So P squared over 2m. Then afterwards, the P, the momentum, you substitute with h over lambda. So you replace P with h over lambda, 2m. So you get the equation of h square, Planck constant square, divided by 2m lambda square. Okay, so this one is electron. But since they have the same wavelength, lambda and lambda here, we don't need to differentiate between them. So you don't need to write lambda photon, you don't need to write lambda electron. But for this mass over here, you have to be very clear, this is a mass of electron. But technically, even if you don't write it, it is actually quite obvious because photon is light is massless. So photon, there's no mass to it. So if there's no mass to photon, this mass can only be the mass of electron. So it will not be confusing at all. Okay, so we can put in this relationship inside. So h squared divided by 2 mass of electron lambda squared. Okay, so I think it's okay to manipulate the equation a little bit, cross out things that are similar to each other. So hc over lambda multiplied by 2 mass of electron lambda squared divided by h squared. So you can see that the h here can cancel, the lambda here can cancel. So you can get equation of 2 mass of electron multiplied by c multiplied by lambda divided by h. Okay, proceed to substitution. 2 times 9.11 times 10 to the power negative 31. C is the speed of light, 3 times 10 to the power of 8. The wavelength that you use is 10 nanometers, so 10.0 times 10 to the power negative 9. Divide by the Planck constant. The Planck constant is 6.63 times 10 to the power negative 34. Okay, so if you substitute everything inside, I believe you get an answer of, double check everything, 8,244, somewhere around there. Okay, so that's the ratio. So you can see that if you compare the energy of photon to the energy of electron, the photon will have around 8,000 times more energy compared to the electron. So the photon is definitely more energetic compared to the electrons. Okay, so you can actually continue this argument to the next question, because the next question says, in view of your answer to part A, which says that photon is more energetic than electrons, which will be less damaging to the specimen you are studying, photons or electrons? So we can know that if the particle itself has less energy, then it will not transfer that much energy to the specimen. Okay, how do I study a specimen is by shining the light onto the specimen, or we are shining the electron beam onto the specimen. So if we shine light or electron beam onto the specimen, those light photons itself carry energy, and those electron also carries energy as well. So when they are being incident onto the specimen, what they do is they impart the energy on the specimen. Okay, so they transfer the energy from the photons or from the electrons to the specimen itself. So if they receive the energy, if the energy is received, it will cause the specimen to experience some kind of heat up. Okay, so heat up is actually quite dangerous when we talk about biological specimen, because it can cause a protein to denature, or it will cause mutation to occur. Okay, so those kind of issues will cause damage to the biological specimen. Okay, so the more energy that these particles have, the more damaging it will be to the specimen. So since we know that photon on the same wavelength as electron, photon possess much more energy, it will cause greater damage to the biological specimen compared to the electron. Okay, so we can say, since photon is much more energetic compared to the electron, okay, photon will be more damaging to the specimen. Okay, so the idea is, again, more energetic, you transfer more energy to the specimen, more energy received by the specimen, a greater probability of it experiencing denature of protein or mutation, gene mutation, those kind of things might occur due to that energy received. Okay, you ionize, causing free radicals, and free radicals causing all types of things. Okay, you can learn about the details in your biological lesson. So basically that's it. Okay, it is showing you another advantage, another significant advantage of using electron microscope, because when you're using electron microscope, right, it is actually less damaging to the biological specimen compared to the usual optical microscope.